Welcome to Lecture 7.4, Divisibility and Factorization. In this series of lectures, we've learned about rings, and a ring is in some sense a generalization of the familiar number systems like the integers, the real numbers, and the complex numbers, where we are allowed to add, subtract, and multiply, though not necessarily divide. Two key properties about these familiar structures are, first, multiplication is commutative, and second, there are no zero divisors. Well, other than 0, obviously. So here is a blanket assumption that we will make throughout this lecture and the next one. So unless we explicitly mention otherwise, R is assumed to be an integral domain, and we will define R star to be the ring without 0. So in other words, R has these two properties. Multiplication commutes, and there are no non-zero zero divisors. Now back to things that we learned growing up in school. The integers have several basic properties that we usually take for granted because they're so simple. First of all, every non-zero number can be factored uniquely into primes. Second, any two numbers have a unique greatest common divisor and least common multiple. Again, I probably should say non-zero here. And finally, there is a Euclidean or division algorithm which can find the GCD of two numbers. Surprisingly, these simple properties need not always hold even in integral domains. We would like to understand this better, and it's going to be the focus of this lecture. Let's start with a very simple definition, which we know from the integers, but we can extend it to integral domains. If A and B are elements in a ring R, then say that A divides B, or that B is a multiple of A, if B equals A times C for some element C in the ring. We write this with a vertical bar, so this means that A divides B. If A divides B and B divides A, then A and B are said to be associates. And we write this using this little equivalence symbol right here. Let's do some examples. In the integers, n and negative n are associates. In the ring of real-valued polynomials, r bracket x, f of x and c times f of x are associates as long as c is non-zero. That's because c has a multiplicative inverse in this ring, which is just 1 over c. In any ring, the only associate of 0 is itself. Finally, the associates of the multiplicative identity 1 are the units of R, and that holds in any ring. Well, actually, I should say any integral domain, because that's the blanket assumption here. Here's a simple proposition, which I'm going to leave on the homework. This says two elements, A and B in R, are associates if and only if A equals B times U for some unit. So in other words, if they differ by multiplication of a unit. This defines an equivalence relation on R, and it partitions R into equivalence classes. Think of equivalence classes like families. If A is in the same family as B, then B is in the same family as A. And if A and B are family members and B and C are family members, so are A and C. One quick observation to note is that units divide everything. In other words, if B is in R and U is a unit, then U divides B. And let's see why that is quickly. Well, B we can write as U times something else. Well, what's that something else? Well, it's U inverse, which exists because U is a unit, times B. So that means that U divides B, or equivalently, B is a multiple of U. Next, if B is not a unit, but the only divisors of B are the units and associates of b, those things will always divide b, then we say that b is irreducible. Here is a similar definition that turns out to be the same as being irreducible in the integers, but not necessarily in all integral domains. It says an element p in the ring is prime if, first of all, p is not a unit, but next, anytime p divides the product of two elements, say a times b, then p must either divide a or divide b. So let's do two examples of this. Let's start with the integers. So let's take p equals 6. Now you know this is not prime, and that's because 6 divides 12, which is 3 times 4, but 6 does not divide 3, and 6 does not divide 4. So this is not prime. Next, let's try p equals 5. Now I claim that anything that 5 divides, let's just pick something, pick negative 30. No matter how you try to factor it, you can factor it as 2 times negative 15, or you can factor it as negative 6 times 5. It's always going to be the case that 5 divides one of those two numbers. Here it divides negative 15, here it divides 5. And that's because p is prime. That's what it means to be prime. Now, again, if you think about what irreducible means in the integers, you'll realize it's the same thing as being prime. But I'll tell you now that for general integral domains, one of these things is stronger than the other. In other words, let me ask you, see if you can figure it out. Does being irreducible imply being prime? Or does being prime imply being irreducible? Well, I'm about to tell you, so if you want to figure it out, pause the lecture. Okay, ready? Here's the answer. Proposition. If p is a non-zero prime number, then p is irreducible. To prove this, let's just suppose that p is prime but not irreducible. We will arrive at a contradiction. So because p is not irreducible, we can write it as a product of two non-units, a times b. And so p divides a times b, trivially, it's 1 times ab. So it must divide either a or b because it's prime. Doesn't matter which one it divides. Then, without loss of generality, that's what this w log means, we can say that p divides a. And so a equals p times c for some c in the ring. So let's now plug this into the a up here. So p equals a times b, and we can plug p times c in for a. So we get p times c times b. Now we can rearrange the parentheses and write this as p times cb. So now we have p equals p times something else, cb, so cb must be equal to 1. And that means that b is a unit because c is its multiplicative inverse. So formally, this means that cb is equal to 1, and thus b is a unit, which is a contradiction to the assumption that neither a nor b were units. Since I said that being prime and irreducible are not the same thing, and you should suspect that there are irreducible elements that are not prime. But this is obviously not the case in the integers, so you have to go into more unusual rings to find them. So here's one example of the ring R negative 5, which is a set of elements of the form a plus b times the square root of negative 5, where a and b are integers. Or if you prefer, you can think of this as a plus b times 5i. This is an example of a ring of algebraic integers, and we will study these a lot more in the next lecture. In this ring, 3 obviously divides 9. It's equal to 3 times 3, but there is a cute little way to factor 9 as 2 plus root negative 5 times 2 minus root negative 5. It's not hard to check that 3 does not divide 2 plus root negative 5 or 2 minus root negative 5. There's clearly no way to multiply 3 times something like this to get either of those. And it's also not hard to check that 3 is irreducible. There is no way to write 3 as a product of multiple numbers of this form. Therefore, as I said, 3 is irreducible in r minus 5, but it is not prime. Because again, it divides a times b, but it does not divide a or b individually. When irreducibles fail to be prime, like in this example, we can lose nice properties like unique factorization. Things can actually get really bad. Not even the lengths of factorizations into irreducibles need be the same. For an example of this, consider the ring r equals z bracket x squared and x cubed. So to motivate this, imagine the ring z bracket x and y. These are all polynomials in x and y. So the monomials are of the form k times x to the I times y to the j. So in this ring, you can think of the variables as being x squared and x cubed. So in here, the monomials are going to be of the form k times x squared to the I times x cubed to the j, or just k times x to the 2I plus 3j. Now, it's not hard to see that this ring here does not contain x. So x is not in R, but it's easy to see that x squared is in R, as is x cubed. And every integer can be written as 2I plus 3j. Every integer greater than 1, that is. So x to the 4th is just x squared times x squared. X to the 5th is x squared times x cubed. X to the 6th is x cubed times x cubed. X to the 7th is x cubed times x squared times x squared. And all of these things are in R. So you can think of this ring as the polynomials with integer coefficients in the variable x, except you can't have any terms with x to the 1st. So in this unusual ring, x to the 6th can be factored as x squared times x squared times x squared, so into the product of 3 irreducibles, but it can also be factored into the product of 2 irreducibles as x cubed times x cubed. The element x squared in R is not prime in the ring because x squared divides this product, a times b, or x cubed times x cubed, but it does not divide either irreducible, does not divide x cubed in the ring because x is not in the ring. So here's an example of an element that can be factored into irreducibles not only in 2 different ways, but involving 2 different lengths of irreducibles. Fortunately, there is a type of ring where such bad things don't happen. For this, we need a definition first. An ideal I generated by a single element A is called a principal ideal. We denote this, as we usually do, by just putting parentheses around the generator. Note that this is analogous to, in group theory, cyclic subgroups. Those are subgroups that are generated by a single element in a group. Next, if every ideal of R is principal, then R is a principal ideal domain, or a PID. So notice that R itself is an ideal, so it has to be generated by a single element. So this truly is the ring theoretic analog of the concept of a cyclic group. Now, we didn't prove it in the lecture. I think I put it on the homework, but cyclic groups have the property that all subgroups of them are cyclic as well. So same with PIDs. That's built into the definition, but it's still there. Every ideal is generated by a single element. Although it's slightly different because we're not talking about subrings being generated by single elements. We're just talking about ideals. Let's do some examples. The following are all PIDs. I will state this without proof, although some of these we will come back to later. First of all, the ring of integers is a PID. Next, any field is a PID. And this is actually pretty easy to see. Clearly, the zero ideal is generated by one element, namely 0, but since every non-zero element in a field is a unit, then any non-zero ideal of a field contains a unit, and therefore is the entire field. And that's generated by 1. So fields only have 2 ideals, so they are trivially principal. And finally, a polynomial ring in one variable over a field is a PID. We'll learn more about this in the next lecture when we study Euclidean domains. As we will see shortly, PIDs are very nice rings. Here are some properties that they enjoy. First, pairs of elements always have a greatest common divisor and a least common multiple. Every irreducible element is prime. So in a PID, being irreducible and being prime are exactly the same thing. And finally, every element factors uniquely into primes. When I say uniquely, I mean up to associates, because obviously you can write 6 as 2 times 3, or negative 2 times negative 3. Let's look into greatest common divisors and least common multiples in more detail. We'll start with the ring of integers because we're familiar with them. So first I want to prove that z is a PID. So to do this, I'm going to take an arbitrary ideal I, and I claim that this ideal is not only principal, but I can tell you what it's generated by. Namely, if I take A to be its smallest positive element, then A generates I. To prove this, first let's pick any positive number in the ideal and let's call it B. Then we can use the division algorithm, which is just a fancy term for something that you learned in elementary school, to write B as a multiple of A plus R, where R is strictly less than A. So an example of this, let's suppose that A is equal to 5 and B is equal to 12. Then we can write 12 as 5 times 2 with a remainder of 2. Or if instead A was equal to 12 and B was equal to 5, then we could have written 5 as 12 times 0 plus a remainder of 5. So it doesn't matter which one of these, A or B, is bigger, we can always do this. Next, we can solve for R. So we can write R as B minus A times Q. Oh, B is in the ideal by assumption. And since A is in the ideal, so is AQ. So this difference is in the ideal. In other words, R is in the ideal. Well, R is strictly less than A, which is the smallest positive element of the ideal, which forces R to be equal to 0. Therefore, B is equal to Q times A, which is in the ideal generated by A. So we took an arbitrary positive number in the ideal, I, and showed that it is in fact in the ideal generated by A. And we could do the same thing with a negative element. So therefore, the ideal I is in fact generated by the single element A. Now we need some more definitions. A common divisor of A and B in R is an element D that divides A and divides B. Moreover, D is a greatest common divisor, or GCD, if the following holds. If for all other common divisors C of A and B, C must divide D. So you may be looking at this and thinking, well, why didn't we just write C is less than or equal to D? Well, there are several reasons. First of all, we would have to put an absolute value sign around these because one of them could be negative. But more importantly, there need not even be a concept of absolute value or even of less than or equal to in general integral domains. For example, in the ring R negative 5, which we saw earlier, we have elements of the form a plus b root negative 5. What would the absolute value of an element like this mean? Or what does it mean for one element to be less than another one? So instead, we have this condition. We say that any other divisor of A and B must divide D. So you can think of C as being less than D because it divides it. Next, a common multiple of A and B is an element M such that A divides M and B divides M. So again, no surprise here. Moreover, M is a least common multiple, or LCM, if for all other common multiples N of A and B, M divides N. So every common multiple N is bigger, at least as big as M. Notice this is analogous to what we did up here for GCDs. As mentioned earlier, PIDs have a number of nice properties, and here's one of them. If R is a PID, then any non-zero elements A and B have a GCD, and we write this as GCD of A and B. Moreover, this GCD is unique up to multiplication by associates, and it can be written as, I'm going to call this a linear combination of A and B, though I'm slightly abusing notation there, though you know what I mean, right? It can be written as XA plus YB for some X and Y in R. To prove this, the first step is to show existence, that there is such a GCD. So let's start with the ideal generated by A and B. By definition, that is the set of elements of the form U times A plus V times B. So, as I like to say, the linear combinations of A and B. Since R is a PID, this ideal is actually generated by a single element, let's call it D, and that element also has the form XA plus YB. In other words, it is a linear combination of A and B. Since A and B are in the ideal generated by this mysterious D, then D must divide A and D must divide B. So in other words, D is a common divisor of A and B. Now we have to show that it is in fact a greatest common divisor. So let's take another divisor of A and B. Let's call it C. So this means that C divides A and C divides B, so it clearly divides X times A plus Y times B, which is equal to D. And that's what we needed to show. Therefore, D is in fact a greatest common divisor for A and B, because any other divisor C divides D. Finally, for uniqueness, if D prime is another GCD, then because it's a greatest common divisor, the other divisor D must divide it. But also, D is a greatest common divisor, and because of the greatest part in here, all other divisors, namely D prime, must divide D. Therefore, D and D prime divide each other, so they are associates, and that's what we had to prove, that the GCD is unique up to associates. A corollary of having a unique GCD is that every irreducible element is prime. To prove this, let's take an element P that is irreducible, and let's suppose that P divides A times B. All we have to show is that P divides A or P divides B. So if P divides A, we're done. So let's suppose that P does not divide A. Now P is irreducible, so its only divisors up to multiplication by associates are 1 and P. And if P does not divide A, that means that the only common divisors of P and A are the units. So the GCD is 1. So by the previous result, we may write 1 as a linear combination of A and P. There I am abusing language again just a little bit. But you know what I mean. So I can write 1 as x times A plus y times P for some x and y in the ring. So now I want to multiply this equation on both sides by B. It doesn't matter on the left or the right because multiplication commutes. So B equals xa plus yp times B. So I'm going to multiply this out, and I get xab plus ypb. Now I'm putting the parentheses here so you can see clearly that P divides A times B, that's by assumption, and P divides the second term because it has a P in it. So since P divides both of these terms, then P divides the sum, which is equal to B, and that's exactly what we wanted to prove. That if P divides A times B, and it doesn't divide A, then it has to divide P. Moving on, it's not surprising that least common multiples also have a nice characterization in PIDs. Here's the analog of the theorem on the previous slide, but for LCMs. And I will leave the proof on the homework because it is similar in flavor. If R is a PID, then any pair of non-zero elements have an LCM. Moreover, it is unique up to multiplication by associates, and it can be characterized explicitly as a generator of the ideal I, which is the intersection of the ideal generated by A and the ideal generated by B. You can think of the former as the multiples of A and the latter as the multiples of B, so things in the intersection are the common multiples to A and B. Now that is an ideal, and since we are in a PID, the ideal is principal, meaning it is generated by a single element, and that element turns out to, by this proposition, be the LCM of A and B. Not surprisingly. The next type of ring that we want to study is called a unique factorization domain, or a UFD. So the definition is that an integral domain is a UFD if the following conditions hold. First, every non-zero element is a product of irreducible elements, and every irreducible element is prime. Let's do some examples. The integers is a UFD because every integer n can be uniquely factored as a product of irreducibles, or equivalently primes. And when I say uniquely, I mean up to associates. This is simply the fundamental theorem of arithmetic. It's something that you've probably never questioned because you learned it in grade school. Next, the ring of polynomials over Z is a UFD because every polynomial can be factored into products of irreducibles. This is something else that you know from growing up, and we took this for granted when we studied Galois theory in the previous series of lectures. However, it is not a PID because the following ideal is not principal. So the ideal generated by 2 and x, I claim, is a set of polynomials where the constant term is even. And if you want to see why that is, well then, this is explicitly all polynomials of the form 2 times g of x plus x times h of x. So this second term does not have any constant term, right? And this first term, if there's a constant term, it has to be even. So clearly, every polynomial in here has an even constant term, and I claim that every polynomial with an even constant term can be written like this for some g and some h. And that's not hard to see if you think about it for a few moments. The ring R-5, which we saw in the beginning of this lecture, is not a UFD because 9 can be factored two different ways as a product of irreducibles. 3 times 3, or 2 plus root negative 5 times 2 minus root negative 5. And finally, it's not really an example, I guess, but it's just a statement that we have shown previously that this second property, every irreducible element is prime, which is built into the definition of a UFD, holds for PIDs. In the next slide, we will show that this first property holds as well. And we will do that by showing that every UFD is a PID, and that will imply that both of these hold right away. Here is that statement formally. If R is a principal ideal domain, then R is a unique factorization domain. For the proof, all we need to do is show that condition 1 holds in the definition of a UFD. That is, every element is a product of irreducibles. We've already shown the second condition, which is every irreducible is prime. To do this, we will introduce a concept of a Noetherian ring. This is something named after the German mathematician Emmy Noether. And this says a ring is Noetherian if every ascending chain of ideals, so that means I1 is contained in I2, which is contained in I3, and so forth, eventually stabilizes. In other words, for some k, ik equals ik plus 1 equals ik plus 2, and so forth. Suppose R is a PID. It is not hard to show that R is Noetherian, and I'll leave that on the homework. Next, let's define X to be the set of elements in the ring R, excluding 0 and excluding the units, that cannot be written as a product of irreducibles. All we need to do to finish the proof is to show that X is empty. So let's suppose it's not empty, and let's pick an element, A1, from it. We can factor A1 as a product of two non-units, A2 times B, and at least one of these elements cannot be written as a product of irreducibles. Otherwise, A1 could be written as such a product. So let's just suppose that A2 is that particular element. I mean, possibly both of them are, but let's pick A2, and by definition, A2 has to be in X. Now, the ideal generated by A1 is contained in A2 because A1 is a multiple of A2. And I claim that this inclusion is proper. In other words, that A2 is not in here. Well, why is that? So if A2 were in the ideal generated by A1, then A2 would have to be some multiple of A1. And so what multiple would that be? Well, that would have to be B inverse. Although B is not a unit, so this is impossible. So this inclusion is proper. Why is the second inclusion proper? Well, A2 being in X is not a unit, so this ideal cannot contain a unit, so it cannot be all of R. So now we repeat this process. In other words, we take A2 and we can write that as a product of two things, say A3 and B prime, at least one of these cannot be written as a product of irreducibles. Conveniently, let's call that one A3. So neither of these are units, and A3 has to be an X. So we can now conclude that the ideal generated by A2 is properly contained in the ideal generated by A3. And again, repeat the process. We can find an ideal generated by another element, A4, that properly contains that, and so on. We get an ascending chain of ideals in this manner. Since each of them is proper in the previous one, it cannot stabilize. This is impossible in a PID, and so our set X has to be empty, which means that every element is a product of irreducibles. We'll conclude this lecture with a summary of the different types of rings that we've seen up to this point. So those with the most structure are the fields. These include complex numbers, the rationals, the algebraic numbers, the reals, ZP. Here's a finite field of order 4. Here's one of 256. Here are some that we saw when we studied Galois theory. We could have included the constructible numbers in here and tons more. Every field is a principal ideal domain. However, there are PIDs that are not fields, such as the integers z and polynomial rings over fields. Every PID is a UFD, but there are UFDs that are not PFDs. For example, polynomial rings over Z and multivariate polynomial rings over fields. Every UFD is an integral domain, but there are integral domains that are not UFDs. For example, Z bracket x squared and x cubed and R negative 5. Every integral domain is commutative by definition, but there are commutative rings that have zero divisors and therefore are not integral domains, like Z cross Z or Z6 or 2Z. Even though that does not have zero divisors, it does not have unity, so it is not considered an integral domain. Finally, there are rings that are not even commutative. For example, the Hamiltonians, the n by n matrices over R, or really over any field, and group rings, as long as G is non-abelian. And I should mention one last thing, that I did not include Noetherian in here for several reasons. First of all, you can define Noetherian for non-commutative rings, though you have to distinguish between being left Noetherian and right Noetherian, depending on whether chains of left ideals or right ideals end up stabilizing. And there are rings that are left Noetherian and not right Noetherian, and vice versa. But also, even within the domain of commutative rings, there are Noetherian rings that are UFDs and some that are not. And I think if irreducible elements are prime, then Noetherian rings are UFDs, but if not, then that need not hold. So what that would mean is that the Noetherian rings would, I don't know how to draw this well, would something like this, and I'm sure there are examples of something in here and something in here, but I'm also sure that they're not easy. So due to all those factors, I have decided to not include Noetherian rings into this picture. And these are the most common types anyways. Noetherian, the concept of that is a little bit more advanced and a little more obscure, although it comes up all the time when you get into graduate level algebra and commutative algebra. Finally, in the next lecture, we will look at the Euclidean algorithm from more than 2,000 years ago, and we will see when that can be extended to rings. And this will lead us to the concept of a Euclidean domain, and that will be a type of commutative ring that will fit somewhere in this picture as well. So stay with us.